Hey everyone, in this lecture I'm just going to do an example problem from chapter 21 involving Coulomb's law. So I'll also do another example in the next lecture, but these problems should help you to understand and are similar to some of the problems in the assignment for this week. Just a reminder, the homework assignment for chapter 21 is due by next Wednesday. The reading quiz, which I have not posted yet, will be due on Monday. I'll be posting the reading quiz sometime tomorrow. But let's go ahead and do the example. So in this case, this is example 1 from chapter 21. I want to look at calculating the force on a charge due to other electric charges. So in this particular problem, we're going to do a one-dimensional example. We're going to look at 3 charges along just the x-axis, right? One dimension. So I have a charge Q1 at x equals 0 centimeters, and it has twice the charge of the other ones, right? So I'm writing 2Q. Q could be 5 nanocoulombs, 10 nanocoulombs, whatever the charge is. It'll turn out that it will not matter in this problem. Then I have charge Q2, which is just one amount of charge, 1Q, but it is negative at x equals 3 centimeters. And then the charge Q3, which is the one I want to calculate the force on from the other two, is at an unknown value of x, right? But it's a positive Q charge. And the question is, for what value of x is the force on Q3 equal to 0, right? So what is the value of x at which the net force from these other 2 charges is equal to 0? Where do I have to put Q3 to basically make it into equilibrium so that the forces add up to 0? So just like other forces, Coulomb's law of forces obey what's called the principle of superposition, right? You can add them together as vectors. So the statement of our problem, again, the arrow here means just that it's a vector, is that the force on Q3 is equal to the vector sum of the force of 1 on 3 plus the force of charge 2 on charge 3. And I want them to equal 0. So at this point, we're going to plug in Coulomb's law. Right? So the force here, F13, is going to be our KQ1, Q3 over the distance r squared, which in this case is the distance between Q1 and Q3, and that is x, right? It's the full x value. It is going to be in the positive x direction because these 2 charges, Q1 and Q3, are both positive. They are like charges and they repel. So F13 is to the right in the positive or I hat direction. I'm using the unit vector notation here. So let's go to the force of charge 2 on 3, F23. Again, using Coulomb's law, KQ1, Q2 over r squared, I have K times Q2 times Q3 over the distance between them squared, which is the x minus this 3 centimeters. Right, so I'm just getting this distance between Q2 and Q3 and squaring it. Now, Q2 and Q3 are opposite charges, negative and positive. So the force on Q3 is attractive, and it's going to be pointing to the left in the negative I hat direction. So again, we want these forces to add up to 0. So basically, I end up with this equation, right? And I've plugged in 2Q for Q1, Q for Q2, and Q for Q3. Be aware, right, in this case, I don't have to put in negative Q for Q2. I've already taken into account the direction by making this negative I hat sign here. So in Coulomb's law, once I've determined the direction, I don't need to put in the sign of the charge. I'm just putting in the magnitude of the charge here. All right, well, now you can maybe notice that the Q's and the K's will cancel out. That is divided by KQ squared. 0 over KQ squared is still 0. So eventually what I end up with is basically just this algebraic equation. 2 over x squared minus 1 over x minus 3 squared equals 0. And now I just got to do a bunch of algebra to solve this. First of all, I can add the 1 over x minus 3 squared to make it positive, and then multiply by x minus 3 squared and x squared, and I eventually get this, right? So again, this is just doing some algebra. Then I can FOIL out the x minus 3 squared, comes x squared minus 6x plus 9. Do a little more algebra, right, to get it into the quadratic form here. So this is a quadratic equation, and I can apply the quadratic formula to it, which I did right here, right? X is equal to negative b plus or minus square root of b squared minus 4ac over 2a. A is equal to 1 in this case. But when I do that and calculate the actual values, I get x equals 1.76 centimeters or x equals 10.45. Now, I always get two answers when I have a quadratic. I have to think a little bit about the physics now, though. Which one of these answers is right? Let's go back to our picture, right? Well, certainly the x equals 10.45 centimeters can be correct because I'm outside, I'm greater than x equals 3, which this situation corresponds to. The forces are opposite in direction, so they can cancel out. So I'm thinking, okay, 10.45 centimeters is probably right, but what if I was at x equals 1.76 with my positive Q3 charge? Well, maybe you notice you can never get this to be 0 here because this positive charge will be pulled toward the negative Q and pushed away from the positive 2Q. So these forces, if you're in between the charges, they're both to the right. They can never cancel out. So physically speaking, why do I get this 1.76? Well, this answer would correspond to the case if both of these charges were positive, right? Then this one would repel and you would have opposite charges. And the answer 1.76 would work for that case. But in our particular situation, we have to choose x equals 10.45. Physically speaking, this cannot correspond to the correct answer for these signs of these charges. If I did change this to a plus q, the 1.76 would be my correct answer. But in either case, you can see what I'm doing when I calculate the force on a charge, I just add up the Coulomb forces from the other charges. In the next lecture, I'll look at a problem that is not one-dimensional. It's got 2 dimensions to it, and we have to deal with the vector components. But that's all for this one. And so I will see you in the next